Oops. Good morning. Can you hear me? Good. Thank you. All right. Okay. All right. So before we get started, let's take a look at the syllabus and sort of see where we're at and make sure that we're on our way to where we need to be. Okay. So let's see. We are at Tuesday, January 26th. Okay. So today we're doing Introduction to Equilibrium. And then on Thursday, we'll be doing some calculating of K. And then on Tuesday of next week, we've got the test one review, and there'll be no class on the test one day, which is going to be Thursday, February 4th. So we're looking at about 1.5 weeks until the test is due. I want to remind you that the test can be done at any time up till that day. In other words, you don't have to wait till that Thursday to do it. Okay, so you've got all of this time. I don't think anybody's taken it yet. Now, I want you to remember that the test you're taking is the exact same test as the practice test. You'll just be, your study will usually consist of just doing that again and again and again and again until you understand everything that's on there. Does anybody have any questions so far about what we're doing and what's going to be required? Any thoughts, questions, anything like that? Okay. The homework, sorry, not homework, the extra credit will be due on Wednesday, February 3rd, 11:59 p.m. My advice, get that done early so you can spend as much time as possible studying. And I'd recommend as well getting that test done early rather than later. Okay, let's have a look. Okay, just make sure everybody's got their video on here. It looks like they have. Oh, excellent. Okay. So we're at equilibrium at this point. Now I'm going to pull up part of one of my videos here because that's the only way I can show you this. The app that this video came from, or this video was based on, it no longer exists anymore, I don't think. So it's a good thing that I recorded it. Okay, so the basics of equilibrium. So the products over the reactants gives you this K expression, or it's concentration of products over concentration of reactants. So generally speaking, for any reaction like A, B gives C plus D, the K value would be C to the power of C, D to the power of D. So C to the power of the coefficient, D to the power of the coefficient. Effectively, what you're doing is you're multiplying everything that's on the product side, all the concentrations on the product side, and putting it over the product of all of the reactant concentrations all multiplied together. And that's really all it is. And this gives us an idea of where the reaction is at equilibrium. So in order to illustrate this concept of equilibrium, I'd like to pull up one of my mini lectures here. and it is it's not a bad little video, this one. It is Introduction to Equilibrium, this one here. I'm going to change the share here for a second, so I'm going to stop the share. Give me a second, please. And I want to share sound. Please install this in audio. Okay, well, it's not looking like it wants me to do this. Okay. Hopefully that'll work. All right. You let me know if there's any problems, but I'd like to give you an introduction to products or concentration products. And here we've got a reaction. So if this is a reaction here, I'll actually put the reaction over on the side here. And I think it's 2A gives B, and I think the A's are red and the B's are blue. All right, so let's take a look at what happens with this. Where we're going from 2A to B, and the A's are red and the B's are blue. Let's take a look at how the reaction goes. All right, so we're starting off with all reds here, and again the reaction is 2A gives 1 blue. Now what you can see here is we start off with 80 molecules of red, and we start off with 0 molecules of blue. And eventually, as time goes on, the amount of blue evens out at around, looks like about 20, and the amount of reds is going to even out at something like about 50. Can everybody hear the computer audio? Hang on, let me see. I can't see you, so I'll figure it out in a second.
Yes, we can hear it.
Okay, good. Thank you. Appreciate it. All right. Going to continue on here. Now, what's going on here is that the number of reds and blues is now constant, because you can see that we've got roughly parallel lines going on here. Now, what I want you to do is just follow one of these blues and see what happens to it. I'm following this one. And what we're going to see is that at some point this blue is going to switch into 2 reds. So it's going to react. But at the very same instance in the reaction, 2 reds are going to become a blue. So these are not the same reds and blues that we're seeing here. They're reacting and they're changing, but the number of blues and reds is remaining constant, and that's how we're obtaining this equilibrium type situation. This blue doesn't look like it wants to change, but it will change at some point. And you can see all around it, you see reds turning into blues, you see other blues turning into reds as well. There we go, it's gone now. And what happened was it turned into 2 reds, and then somewhere else 2 reds turned into a blue. And it was almost an instantaneous type situation. And this is what keeps the situation the way it is, with a constant number of reds and a constant number of blues. Okay. Does anybody have any questions? Does anybody have any questions about what you just saw on that video? Okay, so that's what an equilibrium is. It's a dynamic situation. We started out with only, 0 reds and 0 blues. So what happened is the reds turned into blues, and then we've got this constant number of reds and blues. That's equilibrium. And because those concentrations are now constant, it means we come up with a value of an equilibrium constant that is also constant. That's why it's called an equilibrium constant, because it's a constant value. It doesn't change because the concentrations of the reactants and products are not changing. Okay, you can have access to this on your own as well, so you can see this. It's in the mini lectures folder. I'd recommend watching that video. It's not a bad one, and it will give you a much greater insight into the concept of equilibrium. Okay. So here's what we know about K. If K is greater than 1, it means that there's more products than reactants at equilibrium. That's all it means. So we've got the products on top, we've got the reactants on the bottom. If K is greater than 1, it means this value, the top value, must be greater than the bottom value. If K is less than 1, the reverse is true. It means that there's more reactants than products. That's all it means at equilibrium. Now, the thing is that not every situation we deal with is an equilibrium situation. We can also deal with another creature called the reaction quotient, which we call Q. But Q doesn't have to be at equilibrium. So all of the ones we've talked about, the example we talked about so far is we just showed what happens once it reaches equilibrium. But what if it isn't at equilibrium? So let's take a look at that situation. So going back to the video here, I shouldn't have closed it. The concentration. All right, so we're starting off with. So at this point in the reaction, this is the one we just looked at, you'll notice that we start off with reds and blues, but the lines are not constant yet. So this situation right now, when we've just started the reaction, it's not at equilibrium. With all reds here, it's still not at equilibrium right now because the lines haven't stabilized. And again, the reaction is 2A gives 1 blue. Now what you can see here is we start off with 80 molecules of red and we start off with 0 molecules of blue. And eventually, right, so you can see now it has reached equilibrium once those lines become parallel. But between the point I've got here on the cursor and this point, it's not at equilibrium. As such, we can make predictions about where the reaction's going to go as long as we can calculate this other magical value called Q, which is the reaction quotient. The reaction quotient can be used at any time, not just at equilibrium. K only applies at equilibrium conditions. So if the reaction is not at equilibrium, we can get this Q value, and it's not really a coincidence, but the Q value is measured exactly the same way as the K value would be. It's the only caveat here is that these concentrations are not necessarily equilibrium concentrations. They can be, in which case Q equals K, but they don't have to be in order for us to calculate Q. So here's what we know. If Q does equal K, then the reaction is simply at equilibrium. If Q is less than K, then we know the reaction will shift towards the products. And if Q is greater than K, then we know that the reaction will shift towards the reactants. So the explanation for all of that, let's take a look at just very simplistically. So that's our very, very basic Q expression here, products over reactants. And let's say we've got a K value. The K value will be a constant. And then here's what I want you to imagine. If Q is less than K, then you've got to say, and this is the thing about equilibrium, is that every reaction is going to want to get to equilibrium. Every reaction is going to want to get to K. So if Q is less than K, you know exactly what Q is going to do. It's going to get bigger so it reaches K. And what's going to happen here is the product's concentration is going to have to increase and the reactant's concentration is going to have to decrease. Now that's going to happen automatically. If the products are increasing, the reactants automatically have to be decreasing because what's happening is the reactants are turning into products. So if the products are going up, the reactants have to be going down. That's how it is. Does anybody have any questions? Nobody has any questions about this? So if Q is less than K, the reaction will go towards products. If Q is greater than K, then Q is going to have to go down and the reaction will move towards the reactants. Does anybody have any questions? I can't believe nobody has any questions about this. Can you hear me?
So you said
Okay.
that the reaction quotient can be used when at equilibrium and when not at
That's
equilibrium.
correct,
So
Katie.
why would we ever use the equilibrium one then?
Well, we need to know at what point the reaction is at equilibrium, because that allows us to get the value of K to begin with. So that gives us our starting point, Katie. If you don't have K, then you don't know where the reaction is in relation to K unless you've got K. Do you see what I'm saying?
Yeah.
Okay, you'll see an example of this in a second. Okay. Anybody got any other questions? All right, let's take a look. So here's an example. This is very similar to what you'll be doing on the test as well. So you're given a reaction. You can see the reaction up here. 2SO2 plus O2 gives 2SO3 plus heat. That's our reaction. This is what you're given. Everything above this answer, bold answer word here, is stuff that you're given. Now that includes, look what else we're given. We're given the K value as well, right? We're also given a whole bunch of given a whole bunch of concentrations, and these are the ones here. Excuse me. Sorry. So these concentrations, they're just random concentrations of what's in the reaction at a given time, and that's our data. So what we're going to do is we're going to use the reaction quotient to determine if the reaction is at equilibrium at this point with these specific concentrations of SO2, O2, and SO3. So we come up with the Q value, and it's going to be SO3 squared over SO2 squared times O2. The squared here, the 2, matches the coefficients that you're seeing on the SO3 and the SO2. And then at that point, it's just plug and chug. We just plug in the concentrations that we're given in the question to come up with our Q value, which in this instance comes out to be 1002, or 1.0 times 10 to the 3 once we've adjusted for significant figures. At this point, the reaction is not at equilibrium because Q does not equal K. And we only know this because we've been given K. K is 279, and we're told here that we calculated here that Q is 1000, or 1.0 times 10 to the 3. So to answer question A, is the reaction equilibrium? It is not, because Q does not equal K. Does anybody have any questions so far?
So, Dr. Musgrave,
Yes, Lonnie.
for this problem, it
Mm-hmm.
would move in favor of the products.
Well, let's take a look. It says here the reaction is not at equilibrium. Which way will the reaction shift and why? Well, as you can see, Q is greater than K. All right, so Q is greater than K. So what's going to have to happen to Q? Q is going to have to go down. So if Q is going down, what that means is the reactants, or the bottom part here, these have to go up and SO3 has to go down. So Lonnie, it would be the other way. It goes towards the reactants. Do you see that, Lonnie?
Yes.
Okay. Does anybody have any
Yes, sir.
questions about this part? If the reaction is not at equilibrium, which way will the reaction shift and why? Well, because Q is greater than K, it's going to go towards the reactants because we need the Q to become K. That's what happens. Q will always become K. Every reaction we know goes towards equilibrium. That's what all this is predicated on. Any questions? Okay. So this brings us to another concept called Le Chatelier's principle, which dictates what happens if a reaction is at equilibrium and we put some sort of stress on the reaction. Now, the stresses that we're putting on the reaction are going to be as follows. It can be adding or taking away reactants or products. We can change the pressure or the volume of the vessel, and we can change the temperature of the vessel. All of these things will have the effect of putting a stress on a reaction at equilibrium. Now, what Le Chatelier's principle tells us is that if a reaction is at equilibrium and we put some kind of stress on it, then the reaction is going to take measures to compensate for that stress. And it will compensate for that stress in very predictable manners. And that compensation is going to take the form of getting back to equilibrium once you've taken it out of equilibrium. So every stress that we put on this reaction is going to take it out of equilibrium, and the reaction is just going to want to come back to equilibrium. That's all Le Chatelier's principle is saying. And that's what I mean by compensate for that stress. So let's look at the example here. So it says consider the above reaction at equilibrium. So now we're talking about the reaction is at equilibrium. In which direction will the reaction shift when each of the following stresses are applied to this reaction? So by applying any of these stresses, we're taking the reaction out of equilibrium, and the reaction is now going to want to come back to equilibrium by compensating for those issues. So let's take a look. We've got adding SO3, removing O2, so adding a product, removing a reactant, decreasing the pressure of the vessel, or heating the reaction mixture. So these are the four stresses that we're going to look at for this specific reaction. So let's look at number one, and we're looking at adding SO3. So I'm going to again pull up one of my videos here, which is not a bad video to explain Le Chatelier's principle, in my opinion. Let's have a look. Here we go. I'd like now to talk about Le Chatelier's principle, and it basically the effect of adding gives 2SO3. Yeah, I know this looks kind of complicated, but this is what we're doing here. So we're looking at two effects here, adding SO3, removing O2. So I've made up something here for equilibrium. And if it's at equilibrium, if I'm saying it's equilibrium, we can simply calculate the K value by counting the number of SO3s, the number of SO2s, the number of O2s, and just using, you can see the reaction up the top here. You see the reaction here. And all I'm doing is just plugging the numbers that I see here. So that's where the 6 is coming into play. There's 6 SO3s, there is 4 O2s, and 4 SO2s. Yes, there. And if you just count them there, if we do that math, we come up with 0.5625 as being the K value here. Does anybody have any questions about what I've done so far with the K? So what I've done in the next box here is I've added 3 SO3 molecules. Now, by doing that, the reaction is no longer at equilibrium. So we're no longer talking about K, we're talking about Q. So Q now is going to be 1.266 because now I've got more SO3 molecules than I used to have. And I plug those in as 9 squared, I come out as 1.266 for the value of Q. So I want you to remember what's going to happen now if the value of Q is now greater than K. So what's going to happen is the reaction is going to have to move back towards the reactants so that Q becomes closer to K. Does anybody have any questions? if we're removing O2, so what I've done is I've taken the equilibrium situation over here. I've taken away two O2s. You can see now that the Q value becomes 1.125, and that is still greater than K. So again, removing O2 has the same effect. It's going to move towards the reactants so that Q can get closer to K. In other words, the bottom part here has to get bigger and the top part here has to get smaller in order for Q to become K. I'll stop here for a second. Does anybody have any questions?
Dr. Musgrave, I got another
Yeah.
question. I'm sorry.
Mm-hmm.
Would we be able to do the opposite? For instance, like taking away SO2 or adding oxygen?
Let's say we take away SO3, right? I know we're adding SO3 here, but let's say we took it away. What would happen then is that the Q value would become less than K. I mean, we can try this. I'll do it over here, okay? So Lonnie was asking about taking away SO3 instead of adding it. So let's pretend, let's take away 3 SO3s. So if I do that, we'll still have 4 SO2s, and we'll have 4 O2s, and now we'll have only 3 SO3s. And if I calculate the Q value now, it's going to be, well, it's going to be SO3 squared. There's going to be 3, there's going to be 9. Yeah, say, yeah, 9. Divided by 4 squared times 4. Now, let me see. I'll bring up my calculator here. Okay, it comes out to be 0.14 as our answer. Now look at what that is compared to the equilibrium constant. That's 0.5625. Now it's 0.14. So what's going to have to happen? The reaction is going to have to go towards products. So the top numbers are going to have to become bigger in order for Q to get closer to K. And the bottom number has to get smaller. Excuse me. But if products are being formed, then automatically the reactants are going down because the products are made from reactants. Does anybody have any questions? Does anybody have any questions? Okay. So looking at the answers here, adding SO3, the reaction is heading towards the reactants, and that's where the arrow is going towards the left. Q increases, the reaction moves towards the reactants to lower Q. So that's what adding SO3 does. It increases Q relative to K. So adding a product causes the reaction to shift so that the product gets used. So on an intuitive basis, that's what we're really saying. If you add more product, then the reaction wants to use up that product in order to become reactants, and that's why the reaction moves towards the reactant side to use up the product we've added. Removing O2. Removing O2 will also shift the reaction towards the reactant side. Again, Q is going to increase. And from an intuitive point of view, if you remove a reactant, the reaction is going to want to create more reactant to replace the reactant you removed. And it will do that by turning products into reactants. So the reaction moves towards the reactant side. Does anybody have any questions? Okay, so let's look at decreasing pressure And I'm going to do that in the context of looking at all the possibilities for that kind of situation. So there's really two situations we can deal with here. And I'm going to look upon this as being a piston. So you can see that as a piston goes down, what we know is that volume goes down and the pressure is going to go up. Is everybody okay with that? Anybody have any questions about what goes on when you push a piston down? Okay. The opposite effect is volume goes up, pressure goes down. All right, so that's the very basis of what we need to talk about here. So in this instance, well, the ruling that goes with the whole pressure volume thing is that I'll write this. I'll write it down here. When volume goes down or pressure goes up, the reaction will shift to the side of fewer gas molecules. We'll say less gas molecules.
Does that say that it will shift to the side with less gas molecules?
Yeah, when volume goes down and pressure goes up, yes. Probably, hang on, I'm going to shift this around a little bit. This will make it a little bit, hang on. Let's make it a little bit less confusing. I'll move this to the top. So it matches what we've got here. And that way we'll get a little less confused, I hope. Okay. When volume goes up and pressure goes down, the reaction will shift to the side with more gas molecules. All right, so that's what we're going to see. How do we do that? Well, let's look at the reaction itself. And you can see that we've got 2 SO2 gas plus O2 gas on the reactant side. So there's 3 molecules of gas on the reactant side. And on the product side, we've got 2 molecules of gas. So what I want you to understand is, let's look at the bottom case down here. If the pressure, sorry, to look at the top case, if the volume is going down, the pressure is going up, what's going to happen is the molecules are going to get more squished together, and it's going to force the reaction into more towards the product side because the product side takes up less space. Likewise, if we increase the volume or decrease the pressure, then the reaction will shift to the side with more gas molecules in order to take up the space that we're introducing. So that's what you do, is just count up the number of gas molecules on each side. Now this only applies to gas molecules. It doesn't apply to anything else. So I'll stop here for a second. Does anybody have any questions? So for this one, the question was, what happens when you decrease pressure? Okay, so pressure is going down. What's going to happen is the reaction will go towards the reactant side because there's more gas molecules on the reactant side. So if the pressure's going down, it means the volume's going up, and it means that the reaction will shift to the side that takes up more space because we've added more space. Does anybody have any questions? Now, as I just said, this reaction only matters for gas molecules. So if you had, this might not be the best example, but so CaO solid, CO2 gas becomes CaCO3 solid. The only thing you would count would be the gas molecule here. So you'll often see that in the examples as well. You have to really take note of the states you're dealing with as well. You're only interested in gas molecules because they're the only things that have an effect on pressure and volume. The solid's just going to sit on the bottom of the container, not do anything. Whereas the gas molecules are actually going to be the ones affecting the volume and pressure in the reaction.
I have a question.
Yeah.
So I know that like on this example, the CaO plus CO, there's only one gas like on the sides of the arrow, but how do you know like how many there is?
Well, I mean, it would just be one. It'd just be one gas molecule. Then one gas molecule on the reactant side, zero gas molecules on the product side. So there's more
So
gas molecules on the reactant side.
so even though that's a carbon and two oxygens, it's still only one gas molecule?
Yes.
Okay.
You're only interested in the coefficient, Alexandra, not
Okay.
everything else. It comes back to something I had talked about a couple of lectures ago about like Cl2. That's just one Cl molecule joined together, whereas two Cls would be two separate Cl molecules. Do you see what I'm saying?
Yeah.
So only the coefficient matters for that kind of process.
Okay.
All right. Any other questions? Okay. Okay. The next one has to do with changes in temperature. So I'm going to give you two examples here for changing temperature. And also we can talk about where the heat is as well on the reaction. All right, so I'll give you those two situations. So there's two kinds of reactions we talk about. This one is endothermic. And the other one is called exothermic. Now, put very simply, endothermic processes take in heat in order to go, whereas exothermic processes give out heat when they go. So endo means in, exo means out. And so exo, external. So if you're talking about an exothermic process, an example would be if you light up a gas grill, you know it gets hot. Right? That's an exothermic process. An endothermic process, an example would be, it's a fairly simple one, just put an ice cube in your hand. What do you notice? It gets cold. Why is it getting cold? Well, it's taking heat from your body in order to take the ice and melt it into a liquid. That is an endothermic process. So anything that feels hot on your hands or warm is going to be exothermic. Anything that feels cold is going to be endothermic. So that's a very simple way of being able to tell if a reaction you're dealing with in everyday life is endothermic or exothermic. Does anybody have any questions so far? So there's two cases that we're going to be looking at. So we've got a reaction here that's got reactants and products, and let's say they are at equilibrium. Then we can put a fire underneath it. That would be, that's a flame, by the way. That's heating the reaction mixture. And the other case, anybody know what these squares are? Any thoughts?
Ice cubes.
Ice
Ice
cubes.
cubes. That's right. So this is cooling reaction mixture. Now this is where people get confused with this example. It says here for part D, it says heating the reaction mixture. When you're heating the reaction mixture, you're heating the entire thing. See, where people get confused is they're thinking, well, do you heat, which side are you heating? Are you heating the product side or the reactant side? Well, you're heating everything. Now, in this case, we look at the reaction we're given, and you can see where the heat is. So this is an exothermic process. So what that means is, if you're heating the reaction, then you're heating the entire thing. And I would want you to treat heat like a reactant or product. If you're adding heat, it's like adding a product. So adding a product will force a reaction towards the reactant side. And the logic there is that if you're adding heat, then the reaction will want to use up that heat by reacting and going towards the reactant side. So that's how that works. Now, the heat doesn't just have to be on the product side, as I suggested over here. It could be an endothermic process, in which case the reverse would be true. If you had an endothermic process and you added heat, then the reaction would move towards the product side. Does anybody have any questions? So when you're cooling a reaction, what are you doing? You're taking the heat away. So if you were to cool a reaction that was exothermic, then the reaction would move towards the product side. If you were to cool a reaction that was endothermic, then the reaction would move towards the reactant side. I'll say that again. I don't know if I said it properly the first time. If you're going to cool an exothermic reaction, the reaction will move towards the product side because we're removing heat. And if we were to cool an endothermic reaction, we're removing heat, the reaction will go towards the reactant side. Does anybody have any questions? So you're all clear on that, hey? That's surprising. Most people, a lot of people get this kind of question wrong on tests, so I can't believe that everybody understands what I just said. Questions?
How will you know if it's an exothermic or an endothermic reaction by looking at an equation?
Because you're always given the equation, Alexandra, and if heat is on the, I'll get the question in a second, if heat is on the product side, it's going to be exothermic.
Exothermic.
If heat's on the reactant side, it's going to be endothermic. I mean, you'll know because you'll see the heat in the reaction. It will actually be there.
Okay.
All right, let's see. Here's a question here. Oh, thank you. Yes, it is ice. All right. Any questions? Any questions? Any other questions? Okay. So, Bonnie, you're here. I thought I saw you. You're here. Bon, are you here? Bon? Bon. I thought I saw Bon in the thing. No, Bon? Bon Lee? No? Okay. Anyway, Bon sent me a question. He was asking how to do this on the fun quiz or one of the extra credit quizzes. Well, this is how you would do it. Okay. Let's go take a look at the test here. And we'll go through the kinds of questions you're going to see on the test that relate to this. Okay. So for question 12, I think you'd be pretty set on how to do this, but we'll take a look. So you've got 1A plus 2B gives 1C. What you would do is calculate the value of Q, and it would be C over A times B squared. And it would really just be a matter of plugging in those concentration values. I really should have made them molar values. I probably will change that and put M at the end of that. So those should be molar values right there. But I don't want you to put any units on for that. Usually, and actually, well, we don't. You can put a unit on for Q or K, but we usually don't. Anybody got any questions about question 12? Okay. If a reaction A to B is found to have a Q value less than K, which way will the reaction shift? Well, I'll get you to do that question on your own. You'll be able to figure that out. Okay, let's have a look at this one. Consider a reaction below at equilibrium. In which direction will the reaction shift if more B is added? So what I would want you to do there is look at this and say, well, B is on the reactant side. If we add more B, the reaction will shift towards the product side. The logic there is that the reaction will want to use up the B that you've added. So it will move towards the product side in order to make that happen. Anybody have any questions? In which direction will the reaction shift if A is removed? So if A is removed, then the reaction will shift towards the reactant side. And it will do that because the A is being taken away, so the reaction wants to form more A to replace the A that you removed. Does anybody have any questions about number 15?
Can you say that again?
Can you repeat that?
Sure. The reaction will move towards the reactant side because it wants to form the A that you removed. Is that okay? Those people who wanted me to repeat that, are you okay with that? Okay, I'm going to say this.
So you're saying that just because they're taking it away, it's going to try and recreate itself.
Yes, that's
to
true,
even
Katie.
itself out.
Yes, that's right. So you can see why it would move towards the reactant side, Katie.
But it wouldn't be the same if 3 B's were like if it's that B's were removed, would it be the same?
It would. Mm-hmm.
Okay.
Yeah. Likewise, if C's or D's were removed, it would move towards the product side.
Product. Okay.
You with me?
Yeah.
Okay. If you add A's or B's, the reaction will move to the product side as well. If you add C's or D's, the reaction will move back to the reactant side. You with me?
Yeah.
Okay. Does anybody have any other questions about this? Okay. In which direction will the reaction shift if reaction volume is decreased? Now, this is a little bit tricky because you've got to look at the states here. If you remember what I had said earlier, I'm not going to write it down again. I had said that the changes in reaction volume or pressure will only be affected by the number of gas molecules. So if you count the number of gas molecules, how many gas molecules are there on the reactant side? Can anybody tell me?
4.
4. Yeah, not 7. All right, you're just looking at the states here, and G is for gas. So there's 4 gas versus 7 gas. So 4 gas on the reactant side, 7 on the product side. So it says reaction, which way will the reaction shift if the reaction volume is decreased? Okay, if reaction volume is decreased, it will shift to the side that has fewer gas molecules, which would make it the reactant side. Does anybody have any questions about that?
Can you just repeat that again so I can write it down?
Okay. If we count the number of gas molecules on each side, we've got 4 on the reactants and 7 on the products. If we're decreasing reaction volume, it will shift to the side that has fewer gas molecules. I'll say it again. If we're decreasing reaction volume, it will shift to the side that has fewer gas molecules. I wrote this down earlier as well. That means it will shift towards the reactant side. Does anybody have any questions? Yeah, so it's really that simple. You just count up the number of gas molecules on each side, and then you look at the process and determine if it's going to go to the side with fewer or more gas molecules. All right, any other questions about number 16? Okay, number 17. Which way will the reaction shift if the reaction is cooled? Well, look where heat is in the reaction. The heat here is on the product side. It's an exothermic process. So I would want you to treat the heat as a product, which means if we're cooling the reaction, what are we effectively doing? We're removing heat. So we're moving a product, which means the reaction will shift towards the product side. Anybody got any questions?
So if the heat is on the product side, it'll just shift towards product side.
If it's cooled, Alexandra, yeah. If you were heating the reaction mixture, it would be the opposite. It would go towards the reactants.
Okay, so if the question is if it says the reaction is cooled, then it's towards the product, but if it's heated, then it's towards the reactant.
No, it depends on where the heat is in the reaction, Alexandra. If the heat is on the product side, yes, that's true. If the heat's on the reactant side, the reverse is true.
Okay.
You've got to treat the heat as a reactant or product. In this case, it's on the product side, so we treat it as a product. So you look upon the addition of heat, heating the reaction, as being adding a product, and the removal of heat or cooling it as being removal of product. And if the heat was on the reactant side, then you would be, again, cooling would be removing a reactant and heating would be adding a reactant if the heat was on the reactant side. Is that clear?
Yes.
I hope it is. I know a lot of this is confusing. It's a matter of just getting it straight in your head. And I think one of the best ways to do that is to continually do these questions until you're getting them right on a regular basis. That way you'll know that you do understand what I'm talking about. Does anybody have any other questions about this? Does anybody have any other questions about this? All right. All right. Well, that's pretty much all I had wanted to cover today. So we'll leave it there. It's Tuesday. Yes, I'll see some of you in lab pretty soon, I imagine. I hope. And I will catch the rest of you on Thursday, bright and early. If anybody wants to hang around and ask me questions, they certainly may. I will talk to the rest of you later on. Thanks for coming this morning. I'll see you.
Thank you.
Thank you.
Yeah, no worries. Thank you.
I have a question because I missed the first day of class. You said at the beginning of class the extra credit quizzes.
Mhm.
Where are those located?
Let me show you. I'm still screen sharing. I'm going to stop recording though. Okay.
Okay.
Give me a second.